On.
Oh, it's on. Okay. Oh, in that case, we'll get started. Okay. Right. So homework. What? 3, 2, whatever. 2 is due today. How many of us have finished? Not bad. This one apparently was very tricky. Sorry, tough cookies. Yeah, sometimes they're hard. You know, you don't have to finish these. There are a lot of problems in this class, and they're not worth that much for your degree. So you should think of it as an opportunity to think about really interesting stuff, rather than like a stressful, must-finish everything thing. And if you've ever been in my office hours or posted something in the Piazza, you've no doubt noticed that I'm basically happy to give away the answers. What I care about is that you're learning from these things, really. So don't think of it as a stressful thing. Think of it as like interesting, cool stuff. Okay, so there were 2 homework problems on your homework that's due tonight at midnight that seem to have everybody tripped up. So I thought we'd spend about 2 3/4 minutes thinking about these problems before moving on. Let's see here. So problems 3 and 4 on your homework that's due today are all about applications of eigenproblems and least squares and so on. Right? Incidentally, problem 4 is like the foundation of a large part of machine learning. So it's worth knowing. But anyway, so I'd say the problem that tripped everybody up the most is this thing about Mahalanobis metrics, right? So this is a weird problem, because somehow when we think of eigenvector problems, we think of eigenvectors. And that's not what comes out of this, right? Our unknown here is a matrix, right? So in this problem, right, you have a bunch of data points, a bunch of pairs, right? Xi, yi, right? And the idea is that somehow these xi and yi should be close in some metric, right? And so if you have the proper metric matrix M, then you want this number minus yi. You want this thing to be approximately 0, right? Now there's a metric matrix that does this really easily. Yeah? What matrix accomplishes this goal? 0. Yeah, if I take all of my distances and just multiply them by 0, this gives me something, well, it's not a really interesting distance metric, but it certainly gives me something that makes these things close together, yeah? And so the whole point of this problem is that this sort of high-level idea of eigenvectors should remind you of sort of when you have a quadratic-looking energy, right? And somehow the minimum is boring, right? Then one way to unboring the minimum is to add a constraint that looks like the norm of something equals 1. Right? This was the point of Monday's lecture. Like we did this several times over. Remember with some registration problems, and we did some principal components analysis, some other stuff. Right? Basically, each time what ended up happening, we had some kind of quadratic energy. Right? I think I can give away part of this problem without disappointing too many people. Right? So if we have a bunch of xi's and yi's that we want to look similar, probably the most reasonable thing, given what we know in this class, is just to take the norm of their difference, right, scaled by this m, and just sum them all up. Just be careful not to norm. Yeah. So this is probably the energy we want to minimize, yeah? And thankfully, today during my office hours, I saw this on a lot of people's paper. But then the problem is that this thing has a minimum and it's 0, right? We just showed it, right? You take m equals 0, and this just zeroes everything out, and norms can't be negative, so we're done. But that's not an interesting metric. So the question is, now you need to say, okay, you want to minimize this thing, right? Such that, and then we need an appropriate constraint here. Okay? And I don't want to give away the rest of this problem because I have a feeling people will be banging their heads against the wall and it's not fair to them to give the rest of it away. Sorry. But what I encourage you to think about is that M is just a pile of unknown things, right? So for example, if M were 2 by 2, it would look like M1, 2, 1, M1, 2, M2, 2, right? But you know, usually when we solve eigenvalue problems, right, we remember on Monday's lecture we talked all about how if we see this thing, right, we secretly know that this problem is just asking for an eigenvalue of A transpose A. Right? This is a pattern that you should just have in your head, right, without having to go through the KKT or the Lagrange multiplier things every single time. Right? We did this calculation a bunch in class. And so the question is, okay, so what is this really doing? Well, you can think of this, right? So we've expanded this thing out a bunch of times, right? And he's just X transpose A transpose A times X, right? It's just a quadratic form. This is just some quadratic thing in the elements of X. right? So any energy function that looks like a quadratic thing in your unknowns secretly can be written in this form, even if you didn't do that. And similarly, what is this 2 norm, right? I can square it without changing anything. We've argued that a few times now. Well, this is just equal to the sum of all of your unknowns squared. So my hint for you guys is if your unknowns are in a matrix like this, does anything change? No, math doesn't care how you store your unknowns. All math cares about is that you have a quadratic thing subject to other quadratic thing equals 1. Right? And that's the most general pattern you should use to say, oh shoot, that's an eigenvalue problem. Right? And so anyway, so that's your hint for this problem. For some reason this seems to really confuse people. By the way, I tend in my problem sets to make lots of use of things we do in lecture. And so for example, like the 4th problem in this problem set, I discussed Tikhonov regularization lecture, and apparently it's slightly different from what Wikipedia defines it. Obviously you should use the one that I defined because I've made the problem set, right? And it turns out that problem is true regardless, but it's a little bit trickier. But yeah, so I would go back through the lecture, and remember, so we sort of want the norm of something equals 1, so go back down our laundry list of norms and find one that kind of makes sense here. Yeah? So that's the sort of reasoning that I want you guys to apply in this class, right? We sort of have these high-level patterns that you should keep seeing, right? Like when you want to solve a least squares problem, you're basically just minimizing a quadratic energy with a matrix and a vector, right? And when you want to solve an eigenvalue problem, you're doing the same thing, but with the constraint that the norm of something equals 1. Right? These are the patterns that matter. Remembering the details of like QR factorization with household or whatever the heck, givens, rotations, is not as important because honestly MATLAB does that. What MATLAB doesn't do is tell you which of these is relevant to the problem you're trying to solve. Yeah? So anyway, there's our high-level pep talk for the day. I know this class is hard, by the way. I've been there. I'm hoping it will get easier for you as you get used to this kind of funky notation and all this vectorized stuff and factoring matrices and pushing around every once in a while. And until it does, come to office hours, get my help, get all the TA's help, and we'll get you there. And by the end of this, my goal is that if you take CS 229, 231A, 221, any of these other ones, which is basically just a bunch of sort of minimize this energy subject to this constraint, right? That's like all of those classes I just summarized in a sentence. You'll be able to just do this and like dominate. Okay? So I promise it's worth it. And this is used all over the place. Even like, maybe not 248, but certainly some of the 348s use this kind of stuff. Cool? There's your pep talk. You should be excited. You're learning really neat stuff. And I know it's hard, but that's life. Okay. So, today we're going to talk about how you actually compute eigenvalues, right? So the last lecture, hopefully now you all believe me, that eigenvalue and eigenvector computation is like a super exciting, useful thing, and now we have to actually do it. Yeah, so we're going to start today, and I'm betting we're not going to get to the end of today's lecture, so we'll continue on this coming Monday, but that's okay, because I got some reserved stuff at the end of the class. Cool. So for now, our setup is going to be that we have a symmetric matrix A. And he's got eigenvectors. We're going to use X today to refer to eigenvectors. And those are the things we're trying to find, and the corresponding eigenvalues lambda. Right? And it's going to be useful for us to number off the eigenvalues by their norm. Right? So lambda 1 is going to be the eigenvalue with the biggest absolute value, and then we're going to sort the other way. Right? We number any way we want, because this is the theoretical part of my lecture. So first of all, for Monday's lecture, because A is symmetric, what do we know about the eigenvectors? Wait. They're real. Yeah, the eigenvalues are real. And what do we know about the eigenvectors?
Yeah, undisconnected.
It's you got a full set. There are n eigenvectors, and they're all linearly independent. And we know one more thing. They're orthogonal. Yeah, exactly. Cool. And this theorem has a name. Remember, it's called the spectral theorem. This is the crowning result of this little chunk of linear algebra if you're a theoretician. And in fact, in functional analysis, the spectral theorem comes again to play when you talk about Fourier analysis, when you talk about, elliptic operators, all kinds of stuff. The spectral theorem just keeps coming back, right? It's this sort of, somehow, positive, definite, symmetric things are just super nice. And so we're going to take advantage of that today to begin with, and then we're going to go back and do our homework and say, like, okay, what happens when A isn't symmetric, right? In fact, it literally might be on your homework. Cool. So what's going to be our main tool today for understanding eigenvectors and eigenvalue matrices is we're going to say, okay, well, because A is symmetric, we know that any vector V in Rn can be written as a linear combination of the eigenvectors of A, right? In other words, the eigenvectors of A form a basis, a very special basis for Rn. And some of this basis is really handy, right? Because what happens when I multiply V by A? Well, instead of having A times X, now you're just going to have lambdas times X's. And somehow now we've separated out these different modes by which our matrix can mess with Rn. Cool? So this is going to be our big trick, kind of the high-level idea of a lot of the things we'll do today. And in particular, let's say that I have probably you guys, a lot of people might have seen this trick before, but let's say that I have this vector V that I've written, you know, in terms of all the x's, and I can just keep hammering them with the matrix A. Right? I can do it k times. So in particular, let's do it one time. So what is AV? Oh, so I'm sorry. So V, I'm going to write as the linear combination of the xi's, right, with coefficient ci. Right? Hopefully we're cool with the sum instead of the dot dot dot. That'll get kind of cumbersome. So right. So what is AV? Well, it's the sum over I of ci times AXI. Yeah, just by linearity. And what is AXI? Come on, you guys should all be speaking up. But what is XI? XI is an eigenvector, so what is A times XI? Yeah, we're going to have an interactive lecture today. I'm going to like literally stop and tell people answer my question. The entire piece. Okay. All right. So now, what is A squared times B? Well, the A's are going to move in here. You're going to get another lambda. Yeah. So in the end, A squared times B equal to sum I, ci, and I squared. That's I. Now, I hope you all believe me. And in fact, right, let's just do a little bit of erasing to get the board space left. What is A to the k times B? Well, all you do is you take your eigenvalues and you raise them to the kth power. Right? And this is why this is a very nice decomposition of your vector V. Yeah? So why would I do this? Well, remember that I strategically told you that A1, or rather lambda 1, is the biggest eigenvector of our matrix A. Right? So let's just for fun, we can say, okay, let's factor him out. Lambda 1 to the k. That's the sum over I, ci, lambda I over lambda 1. K. Oops, that's a k. Thanks. Yeah? So all I did was multiply and divide by lambda 1. You can see that that's the same as this expression here. I just wrote it with dot 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 instead of with the sum. Okay. So in fact, let's separate this slightly more. And we'll do lambda 1 to the k, and then we'll say, we'll remove the first term, which is c1 times x1, right? Because the lambdas cancel for the first term, plus the sum I equals 2 to, whatever, n, lambda I, lambda 1 to the k, x. Yeah? Okay. So for now, let's assume that our eigenvector, or that our matrix has all unique eigenvalues. Right? And we sorted our eigenvalues in decreasing order. Right? So in particular, lambda 1 has the biggest magnitude of any of the eigenvalues of A. Yeah? So then what are all of these numbers? What do they satisfy? Yeah, it has -1, is strictly less than that, is strictly less than 1. Yeah? So what happens if I take k to be really, really big? This number is some number between -1 and 1 to a very high power.
It goes to 0.
It goes to 0. Yeah? So in particular, so A to the big times B is going to be approximately what? Well, that's going to be approximately lambda 1 to the big times C1 B1. Or B. No. Next one. Gosh darn it. I'm not a big. Okay. Yeah, you believe me? Does all the other terms go away? have our first algorithm for computing eigenvalues. Couldn't be easier, right? What did I show you? I showed you that if you take a high powers of k, it's approximately just the first eigenvalue to the k times the first eigenvector, right? And this again is assuming at the very least that the biggest eigenvalue is positively bigger than the second one. Yeah. So in particular, what happens? Well, what's our simplest algorithm for finding at least the largest eigenvalue of A? Well, I can write an iterative scheme that randomly chooses v0, just any old vector in space, right? And then just keeps hammering away at this thing with the matrix A. It's just computing this, right? A to the big times V, right? That's all this iterative scheme is doing. You see that? Vk is just A times the previous V, right? In particular, this means that Vk is equal to A to the k, V, you know, with the appropriate hats. So if I keep doing this for long enough, eventually I'm going to recover an eigenvector of A that has the largest possible eigenvalue. Right? And so this is our simplest algorithm for eigenvalue computation. Just run that until convergence. Super easy. I think you could all go home and implement this. And you should. And play with it. Yeah? Of course, there's one question about this algorithm, which was what happens if mod of lambda 1 is greater than 1? Well, so remember that as I run this algorithm, it's going to start looking more and more like this relationship here. And what is lambda 1 to the big in this case? Huge, right? So I'm going to take my first eigenvector and I'm just going to scale him to some ginormous thing, and eventually probably I'll overflow my IEEE floating point stuff. Okay. Now remember that eigenvectors, you can scale them up and down any way that you want, and you don't affect the eigenvector, right? All I care about is I can make v unit length and I haven't changed anything. So how can I fix my power iteration algorithm? Well, it's quite simple. I can make normalized power iteration, where the first thing I do is I take the previous guy and I hit him with A, and the next thing I do is I scale it by his norm. Right? Now what is this thing equal to? Well, it's equal to A to the k times v0, just like before, times just some constant scale factor. We don't even care what the scale factor is, right? Because we're just multiplying this thing by some scalar at every iteration. Cool. This algorithm is perfectly stable, well behaved, gives you the biggest eigenvector of A, the life is good, and we're kind of done, right? You guys can leave now. So there are a couple details missing, which is going to take us the next 2 days. So the first detail is what? So you guys gave me a hard time during my last couple lectures, as you should have, for not explicitly telling you what norm I'm using at any given point in time. Right? And in fact, remember, we spent that whole lecture defining different types of norms, and then I'm like just throwing around this double bar without any subscript on it. What's that about? But my first question to you guys is, what norm should I use here? 2. So I heard a bunch of 2s, and that is an acceptable answer, and another acceptable answer is any norm. And the reason is that all I care about is that this W doesn't get too big, right? So I just want to divide by some notion of length, because that's what's going to keep kicking me back down into somebody's unit circle. Right? So in fact, actually, oftentimes we'll use the 1 norm, or even just the maximum norm, because somehow that's easier to compute than the 2 norm. And it still gets you there. Yeah? Cool. That was our question. Okay. So what have we done so far? We found the one biggest eigenvalue of A. So we're not quite done, right? We want to find them all. Yeah, we've got to catch all the eigenvalues. So how are we going to do that? Well, for one thing, let's suppose that A is invertible. Right? So not only is A symmetric, but A is invertible. By the way, this argument does not hold for asymmetric matrices, because I can't decompose V this way, but there's a simple extension of this argument that does. We're not going to go into the details there. Right. So let's say that A is invertible. So now we have. So we know that V is an eigenvector of A, so AV satisfies lambda, is equal to lambda V. So we can just multiply both sides by A inverse and divide both sides by lambda, right? A is invertible, so we know it doesn't have any 0 eigenvalues. And then you get A inverse times V is equal to 1 over lambda times V. So how do you get the eigenvalues of the inverse of a matrix from the eigenvalues of the matrix itself? You just take the reciprocals. Cool. And in fact, this also follows because remember from last lecture, we were able to write an expression for A inverse just in terms of the eigenvectors of A. And if you look carefully at that, you'll see that there are a bunch of 1 over lambdas in there. That's the reason. Yeah? By the way, on your homework, the homework that went out today, we're going to have a lot of practice with like, just like we can write out the inverse of a matrix in terms of eigenvectors, we can also write the square root of a matrix, which is kind of cool. Right. So anyway, what's an algorithm for finding the smallest eigenvalue of A? By smallest, I mean closest to 0, assuming A is invertible.
Multiply the A inverse.
Yeah, do power iteration on A inverse, right? Because 1 over the smallest thing is now going to be the biggest thing. Yeah? So we have inverse power iteration. Kind of the nicest thing here is that the basic methods for eigenvalue computation are actually way simpler than the algorithms that we've had for Gaussian elimination and a lot of other things. Of course, there's something that I'm hiding under the rug now, which we'll come back to, which is how fast do these things converge. But we can at least prove that eventually they'll get pretty darn close to an eigenvalue. Okay, great. So what do we do? Inverse iteration is exactly the same as forward iteration, but now there's an A inverse there. Now hopefully what you got out of the first 2 or 3 weeks out of CS205 is that applying A inverse is a whole to-do. Right? And in particular, we motivated our discussion, I think in lecture 3, by saying, okay, what if we have to apply A inverse a bunch of times to a bunch of vectors? Maybe we have a tool for that. Man, it's like Ferris Bueller's Day Off in here. Yeah, so if we have to invert A for a bunch of different right-hand sides, right? We're going to solve AX equals B1, and then AX equals B2, and then AX equals B3, right? We're going to compute A inverse a bunch of different times, and we prefer not to have to start from scratch each time, right? We have tools for this, and in particular, one thing we could do, I'll just answer my own questions for now, I guess. We can factor A equals LU, right? Because remember, inverting A, applying A inverse just using Gaussian elimination, takes n cubed time. But if ahead of time I factor A, right, then each application of A inverse now, because this is forward and backward substitution, is n squared time. Right? We want the individual iterations of this eigenvalue strategy to go as fast as possible. Yeah? So what can we do? Well, it's pretty straightforward. How can we make this thing faster? Well, we can factor A equals LU, and we can break our thing, just like we did before, into 2 solve steps to apply A inverse, right? Here, W still satisfies AW equals VK minus 1. Right, I just done it in 2 steps using the LU factorization of A. Right? Yes?
We don't need to compute the inverse in every iteration, right? You just need to compute the inverse for the first iteration and then just product up the matrices.
Okay, so remember from lecture 2, in big text, I said, never ever compute the inverse of a matrix if you don't have to. And this is one of those cases. Writing down A inverse is a very numerically poorly conditioned thing, if you recall.
Okay.
But LU factorization is numerically happy. And in fact, you can do LUP factorization here and be even better if you like. Yeah, so I would not compute A inverse. Especially because oftentimes, so this thing, right, I mean, this is going to go to 0 like an exponential, right, this ratio. So chances are if you have like a 1 billion by 1 billion matrix, you're still not going to need more than, like if you have nice well-separated eigenvalues, you might not need more than 10 iterations to converge, right? But how big is A inverse? Well, it's a billion by a billion, so you've done a lot of extra work putting it. Yeah. Cool. All right, so now we have strategies for finding the biggest and the smallest eigenvalues, and an efficient, well, slightly efficient, still not as efficient as finding the biggest, strategy for finding the smallest. Catherine?
Why are we applying A or A inverse several times when you only need to apply it once to get to the big or the small?
Oh, no. So this, sorry, this was a little bit corny. This is for K, for large K. So as K goes to infinity.
Oh, for several, okay.
Yeah. Sorry, I get a little cute sometimes with lectures, I should be careful with that. That's, when I taught 148, I apparently said wiggle a few times when I was talking about oscillation for Fourier, and this got students really upset. Okay, so now, right, we're kind of on a seek and destroy mission for eigenvalues right now, right? We can find the biggest, we can find the smallest, now we want to find some in between, and there are lots of strategies for this, and we'll talk about a few. The simplest is, okay, so you kind of see the game that we're playing. Right? We start with this matrix A, and now we're going to play with it. Like we replaced A with A inverse, and then ran power iteration again, and we got something different. Right? So now we can say, okay, well, what if we replace A with other stuff, and then we can look at the eigenvalue that you get out, and then relate that back to the eigenvalue of A. You see the kind of high-level strategy here. So, in particular, let's say again, V is a eigenvector of A with eigenvalue lambda, right? Then we know the eigenvectors of the matrix A minus sigma I for any just scalar sigma, yeah? Because what happens when you apply that to V? Well, you just get lambda minus sigma times V, right? Does that make sense? So, what are the eigenvalues of this? Well, they're just the eigenvalues of A shifted by sigma, yeah? So in particular, but by doing that, right, I'm moving my eigenvalues left and right, the eigenvalue that's closest to 0 has now changed. Yeah? So if I have an approximation of the eigenvalue that I'm looking for, one way to actually get closer to it is to say, okay, instead of doing inverse iteration on A, let's do inverse iteration on A minus sigma I for that approximation, right? And we sort of expect that to have an eigenvalue close to 0, right? And that's going to be the one that we're looking for. In particular, right, to find the eigenvalue closest to sigma, right, what can I do? Well, I can just do power iteration on A minus sigma. Yeah. So now we have strategies for sort of, going in there with like some little surgical instrument and saying, okay, I expect there to be an eigenvalue close to some number. I can put that number in and find it. Right? I can also find the biggest eigenvalue and the smallest eigenvalue, and so on. Right? So I can play lots of games with this. All right. So one kind of side note is how could we maybe make this eigenvalue iteration a little bit faster? Right? So remember we have this expression, I also have it over here, I guess, where basically all I've done is I've taken A and raised it to a high power and multiplied it by V. Remember? And then so you get all these ratios back out. So what's going to affect how quickly this thing just starts looking like x1? What term is going to die the slowest? Right? So remember our argument, right? We had all these different terms of this sum, and we basically argue that they all kind of vanish, except the first one, right? And so the sort of higher level question you should ask is how quickly do they vanish, right? So which one's going to vanish the slowest?
Second term.
The second term, right? So what really matters is the ratio between lambda 2 and lambda 1 to understand the convergence of your eigenvalue strategy. By the way, if lambda 1 is a repeated eigenvalue, that's sort of okay, right? Then you can just think of that x1 is going to be the repeated one that's closest to your measure. Anyway, so yeah, so your convergence rate depends on this ratio between lambda 2 and lambda 1, because that's the thing that you're going to take to high powers, right? For example, if lambda 2 equals lambda 1 minus some epsilon, right? Then this ratio, lambda 2 over lambda 1, right, is going to be what? Well, that's just going to be lambda 1 minus epsilon over lambda 1, which is just 1 minus epsilon over lambda 1, right? Ooh, this thing looks really close to 1, right? And 1 to high powers is still 1. Yeah. So one question you might ask is how do you make this, how can you make this strategy a little bit better when you have a pretty poorly conditioned matrix? By the way, in our next lecture, we'll discuss the condition number of eigenvalue problems. Well, one thing we could do would be to modify our matrix A so that that ratio is better. You guys see, this is the same game again, right? We're going to play with our matrix to make our eigenvalue problems easier. Yeah? And we have a way to do that. Namely, we know how to understand the eigenvalues of this matrix, A minus sigma I. Right? This somehow just shifts the eigenvalues of A by this number sigma. Yeah? Well, it's not obvious how to do this, I would say. In particular, this is kind of a chicken and egg problem. Because let's say that I'm doing inverse iteration, right? Then what I really like is that I really like lambda 1 to be as close as possible to 0, right? Because I'm doing inverse iteration, so that's going to make lambda 1 really big. Or of the inverse, yeah. So what I'd like is an approximation of the eigenvalue that I'm searching for, and then I'll shift by that to get it pretty close to 0 in the inverse. Yeah? But we don't have that. But there's a trick we can do for inverse iteration. It's called Rayleigh quotient iteration. And that's, that kind of goes like this. So let's say that I have an approximation of an eigenvector, right? And B naught.
The convergence would be slower for a well-conditioned matrix, right?
What was that?
The convergence would be slower for a good conditioned matrix.
Do I believe that? No, what matters is the ratio of the first to the second eigenvalue. Remember, the condition number sort of looks at the ratio of the biggest to the smallest eigenvalue. So there's a difference there. Yeah, you'll be a little careful.
Because you just said that for a ill-conditioned matrix, it might not converge faster.
Not quite. So what you should think about is if you have inverse iteration, right? And I solve. Remember, I'm going to do a bunch of a minus sigma I inverse. Remember, we don't actually compute the inverse. This is notation for solve a linear problem times vector bk, right? That's what this is going to look like iterating. So let's say that sigma is really darn close to an eigenvalue of a, right? Then what's going to happen? Well, this matrix A minus sigma I is going to have an eigenvalue very close to 0, right? In particular, right, that means this matrix is nearly non-invertible, right? So your individual iterations might be a little bit more difficult to carry out, but I'm not sure that affects the convergence rate. See the difference? Yeah. Cool. All right. So, yeah. But it's good. Keeping me honest. All right. So, anyway, so let's say I have an approximation of an eigenvector, and we'll call him V naught. All right. And now my question is, well, what should be our approximation of the eigenvalue? And of course, me being who I am, I'm going to write this as a variational problem and try and solve it. Yeah? Because what we really want is A times V naught equals lambda times V naught, right? That's our end goal. But now I'm saying you hand me a V naught, that might not be exactly an eigenvector, and I want to find the corresponding eigenvalue. Yeah? Well, one way to do that is to solve an optimization. We're going to say, okay, over all of the possible approximate eigenvalues lambda, I want the one so that A V naught minus lambda V naught is the smallest. Right? It's a reasonable way to look for an eigenvector. In particular, right, this is the 2 norm, and we plug in the square, just like we always do. So let's expand this energy out. Hopefully you guys are starting to see a pattern, right? There's a reason why I chose this treatment of all this material. Because I know 205 moves very quickly, but I thought this is the best way to see the same kind of repeating stuff. Anyway, so applying our favorite simplification here, we get V naught transpose A V naught. Yeah? Minus 2 lambda V naught transpose A V naught plus lambda squared mod V naught squared. Yeah? Hopefully you guys are sick and tired of this computation by now.